This video is one in a series of technical tutorials produced by PlexTech RF Integration.
I'd like to talk to you about the design of laminate PCBs at microwave frequencies. Now, I'm sure that at least some of what I'm going to say will be familiar to a lot of you, but hopefully there'll be some useful snippets in there. So what I'm going to do, I'm going to start by discussing SMT packaged ICs at microwave frequencies. The time was we had to buy little transistors and bond them in with bits of wire and desperately trying to account for the bond wire inductance and bond in little chip capacitors, even to do an amplifier at 2 gigahertz. Today, you can buy SMT packaged microwave ICs up to around 40 gigahertz, 42 gigahertz. And everyone uses them because there's tons of people who can assemble them, and it's convenient and they're reasonably low cost. I'll then discuss the laminate PCB materials. We'll look at using discrete SMT components, capacitors, resistors and inductors, and how you model those and how you can use them up at really quite high microwave frequencies. We'll discuss printed components, Co-adal connectors, very important. There are a lot around. You do need a little bit of care and attention to detail to get the best out of them. And I'll make a few concluding remarks. So this here is a photograph of a 5mm square body QFN 20. Very common style of package, and in the middle there is the IC that goes inside that package. And you can see actually the IC is smaller than the package. Not much of a surprise there, it's not a TARDIS, but it's not massively smaller, and using the package part is a lot more convenient. There's a huge reluctance now from people to use bird eye ICs unless they really need miniaturization. Everybody wants SMT packaged parts. I'm going to pass this around the audience now. This is a little board which has this on so you can see yourselves exactly how big it is. The more eagle-eyed amongst you, those wearing reading glasses, will discover that the chip in that photograph is actually slightly larger in the Y dimension, and that's because it's from the pre-production ICs, but this is the size of the production version. Sorry. The little note there that came up was to remind me what's going to come next. Solid copper base. Now these SMT packaged ICs have a solid copper base, and that's great. It's good thermally, and it gives you a nice low inductance. And it's vital to have low inductance, low grounding inductance for these microwave ICs. And fortunately, with these packaged parts, they're low inductance, but also the PCB. When you're mounting them on the PCB, you have to make sure that grounding inductance on the PCB is low enough, or things will go horribly wrong. Now the ground inductance, the output voltage, part of that goes across the output inductance, and also part of the input voltage goes across that grounding inductance. It's series inductive feedback. If it becomes too high, it will spoil the performance of your circuits. If it's an amplifier, it will make it oscillate. Even if it started out like a perfect amplifier, you get the grounding inductance wrong, you'll get yourself a little oscillator. And this point just summarizes what I've said. Now, there are two main approaches for reducing that grounding inductance. You use an array of closely spaced vias, and if you buy an SMT packaged part from one of the many established microwave IC vendors, you'll see a recommended LAN pattern at the back of the data sheet, and they will have an array of closely spaced vias. The other thing you do is you use a thin substrate height. Most microwave frequency ICs, certainly 20 gigahertz and above, recommend 1/8 thou thick substrates. And the main reason they do that is because it's a good means of keeping the via inductance low. Here's one we prepared earlier. I have a sample of this. I'm going to pass it around. This is for an SMT packaged IC. This is an evaluation board we did for one of our clients, to allow the IC to be measured right at the package planes. And we also prepared some TRL calibration lines so we could calibrate right up to the package. And you can see here we've got an array of 12 vias in there. We've got a substrate thickness of 200 microns, 1/8 thou. Now, so we know we need to keep the grounding inductance low. So two questions arise. What level and grounding inductance can we tolerate? And how do we estimate what we've got? And we're concentrating just on the PCB because that dominates. Well, this graph, I showed this graph previously in a talk I did on microwave packaging. And there are 3 traces here. And the 3 traces are different gains. What we did is we took an ideal amplifier, or a near ideal amplifier, with this level of gain, flat against frequency, with 100 dB return losses and 200 dB of isolation. Now, alas, you can't buy these parts. This is just an S parameter file. But we put that in the simulator, and we wound up the grounding inductance until the return loss degraded from 100 dB to 20 dB. And then we've plotted it here. So I'm not saying that if you go a picohenry above the limit in these traces, things will instantly burst into oscillation. But what I am saying is these are useful guidelines. If you keep the inductance at these sort of levels, you won't go far wrong. Now, take a look over at the 40 gigahertz part of the range here. What you can see is, if I've got a 30 dB amplifier, the inductance I need is vanishingly small. And this really is why, if you go and look at the websites of microwave IC providers, I'm trying desperately not to give any of them free publicity here, none of them have 30 dB gain amplifiers operating at 30 gigahertz in an SMT package, because it's pretty much impossible to mount the thing on a PCB and get the grounding inductance low enough. They tend to be round about the low 20s of dBs. And that's why it works well. That's the sort of gain you can get in there. So we see that the amount of inductance we can tolerate decreases with increasing frequency, and it decreases with increasing gain. Now, what we're going to have now is a first order approximation to the grounding inductance that you can be expected. This isn't an exact figure, but these are useful guidelines. If you follow these guidelines, work out the inductance, and then look at the graph on the previous page, and then I'd be pretty confident you won't have any issues if the two tie in. So a via inductance of a single PCB is around about 0.4 nanohenries per millimeter. And this is pretty true regardless of PCB material. And if you work that out for something like 100 micron gas, for example, you'd get 40 picohenries. In actual fact, the via inductance in 100 micron gas is round about the 25 to 35 picohenry region. So it's not a bad approximation. If we take an array of n closely spaced vias, now you will get some mutual inductance between them, which will degrade or reduce slightly the benefits of those multiple vias. But if you use the figure 1.5 times L via divided by n, you'll get a reasonable approximation to the sort of inductance that you're going to have. So, for example, we take a height of 0.2 millimeters, the 1/8 thou material we've been discussing. That gives you 80 picohenries of via inductance for a single via. If we use an array of 4x4, we'll get 7.5 picohenries. Seems pretty small, and it is. But if we look on here, this is 7.5 picohenries. We see the 20 dB amplifier comes round about 23 gigahertz. And as I say, it won't burst into spontaneous oscillation at a picohenry above this, but that's the sort of level you need to be at. And if you go in higher in gain or higher in frequency, you need to be lower. You need to put in more vias. Another thing you can do, which helps reduce the effective grounded inductance, is to use grounded coplanar waveguide with tightly coupled ground surface on the top side of the board. That helps reduce the effective grounded inductance. So laminate PCB materials. There are lots of laminate PCB materials available now. Low dielectric constants, well-controlled dielectric constants, pretty easy to process. It wasn't too many years ago when if you were making circuits at 10 gigahertz, you had to use alumina. That's what you used, or possibly a PTFE. Now these easy to process laminates are readily available. The typical dielectric constants start at around 3.5, and that's quite useful. You actually don't want too high dielectric constant. You start then to suffer more parasitic capacitances, and the tolerance effects on your PCB are more significant. Both microstrip and grounded coplanar waveguide are commonly used. Now these are dispersive at higher frequencies. That means as the frequency goes up, the performance changes, the characteristic impedance becomes frequency dependent. And in the limit, at very high frequencies, you can get all sorts of substrate propagation modes. So what you need to do is make sure the substrate height is not too large. Now we recommend 1/10 of a wavelength in the substrate material at the frequency of interest. Again, this isn't a hard limit. If you go 2% above this, I'm not saying things will go horribly wrong, but stick to this limit. That's my solid advice. Here's a graph I prepared in Excel. And what you can see, we consider something like a 10 thou substrate here, 250. And we look at alumina, you can see round about 40 gigahertz is where that's good. If we consider a dielectric constant of 3.4 here, sorry, my laser pointer's down, 3.4, you can see if we use an 8 thou substrate, that's going to be dispersion, low dispersion up to about 90 gigahertz. You only run into problems really if you start trying to use substrates that are too thick at too high a frequency. Metallisation. At low frequencies, as you increase the metal thickness, you reduce the loss. There are other reasons to increase the metal thickness. It's always best to have a track that's thick enough to carry the current that you need to put down it. If you're doing power amplifiers, I have seen people do power amplifiers on inappropriate substrates, and the tracks literally vaporize as the RF power goes through them. Literally, they just disappear. You need to pay attention to these side of things as well. I'm not going to go into loads of detail about this, but look at the thermal properties of your PCB, look at the track width, look at your metallisation thickness. If you're running a lot of current or high RF powers, you need to make sure they're adequate. That aside, then at higher frequencies, it's not always worth using thicker metal, because, as I'm sure we all know, there's a tendency for the RF current to flow to be concentrated in the surface, the so-called skin effect. Now the skin depth we define as the thickness of metal through which about 63% of the current flows. And once the metal thickness is more than a few skin depths, then there's not much to win in terms of reducing insertion loss. There's a skin depth for copper versus frequency, and that is in the paper if anyone wants to refer to it. Using a thin metallisation has some advantages. Track definition will be better. Material cost will be lower because you've got less copper. And the processing, the etching time will be lower. So the processing costs will be lower. Now, these last two here, you're only going to really start to notice those in serious volumes, but worth bearing in mind. Surface roughness. Now, for very short interconnect tracks, people largely forget about surface roughness. But if you've got any serious length of track, or you're starting to realise printed components, and we'll come on to discuss those shortly, you have to look at surface roughness. The red trace here is a simulation without surface roughness. The blue trace is with surface roughness of 1.7 microns, which I took off a data sheet for a PCB material. And now this is a 50 millimeter length, so this is a 2-inch length, so it's quite a track for a microwave PCB. And you can see when you're up there at 50 gigahertz, you see that the difference between with the surface roughness is round about, what's that point? It's 0.7 dB or so. So do bear it in mind. Discrete surface mount passives. Now, what we're going to show now is a simplified model of an SMT capacitor. Now, the capacitance here, the series capacitance C, that's the component we want. Unfortunately, we have all this other rubbish as well. The RP, the parasitic resistance, often you can neglect this. However, if you're designing things like matching circuits for power amplifiers, this RP is vitally important, and you're going from a low impedance to a high impedance, and it can really kill you. You have to use really nice high Q capacitors. The series L, LP there, that's the one that really affects the performance of this capacitor and will limit the frequency to which you can use it. And the PCB pads we've simulated there, we've just split the pad into two, treated half of it as a series line and half as an open circuit stub. And this model, it works pretty well up to very high frequencies. And as long as you account for that series inductance, you can use these, certainly you can use capacitors up to surprisingly high frequencies. And you can embed that series LP in with some shunt capacitance, you know, some open circuit stubs, and get those capacitors functioning to very high frequencies. So if we look at what sort of value you might have for this series inductance, for an 0402, it's around about 0.4 nanohenries, and for an 0201, it's about 1/4 of a nanohenry. You use those values, use that model, and it really will work surprisingly well up to really quite high frequencies. We've done this quite a lot. Here is a photograph of a filter we did, and it's a little low-cost filter, little low-pass filter, 6 gigahertz cutoff. You can see we've got some thin series track there, and that's just a little meandered track. You can EM simulate that, but actually you get pretty close just by simulating it as coupled lines. The shunt inductors are 0201. I can't see them myself, but we have some people who are able to solder them on. And what happens is the series inductance of those capacitors and the via means that those capacitors aren't capacitors anymore up at 20 gigahertz. So if you need the rejection extending up there, you also add on some open circuit stubs. Now this effect of that capacitance and its parasitic inductance, they will become short circuit resonant. That will give you a transmission zero, and this can be quite nice if you've got a problematic frequency you need to reject. So as long as we know what these parasitics are, they can be our friends, we can use them to our benefit. So printed components, first thing to say is they're actually photolithographically defined. Printed is a term that people generally use, and it's from thick film processing. We can use open circuit stubs for shunt capacitors, short circuit stubs for shunt Ls, narrow lines of high characteristic impedance for series Ls, and we can do couplers, splitters and filters. This is a branch line coupler we did, and it's about 14.5 gigahertz, and this is in a commercially available product. A couple of interesting things to notice. See, we've not actually put any grounding inductance in. We've used a radial stub. That's a really nice low inductance ground. We've used two 100 ohm resistors on the isolated part rather than a 50 ohm. This helps reduce the inductive effect, and it increases the power handling. You can do other printed components. Edge couplers for power sampling. This one is a coupled line filter. Now, you can make quite nice coupled line filters, but do bear in mind you will get variation with the process. You need to know what that variation is. You need to be able to tolerate it. And so you need this, essentially what this means is you have to design some additional bandwidth on that filter in order to cope with it moving around a little bit in frequency. If you need a coupled line filter with good rejection, then you need to use something like a thin film filter. And we still use these on occasion. So coaxial connectors. You can now buy high performance edge mounted coaxial filters. They're readily available up to 50 gigahertz. There are people now producing ones that you can mount on a board. I think Rosenberger even have one to 110 gigahertz, but it's quite a beast and it's very expensive. But up to 50 gigahertz now, they're becoming readily available. You do have to be very careful with the layout to get the performance to 50 gigahertz. You can be a little sloppy to 20, 30 gigahertz, but if you want to get good performance in that 30 to 50 gigahertz band, you need to pay attention to detail. Ground plane continuity is everything. Here's one. I'm going to pass around two PCBs. I've not left the connectors on because I didn't want to get them, because these are £100 each, and if you drop them, you damage them. These are on some TRL calibration lines, and they're quite nice, these connectors. You can unclamp them, you clamp them back on again, and these are from Southwest Microwave. Other people make them, but in honesty, the best ones we've found are the Southwest Microwave ones. And you can see, well, you'll see on the PCBs a little, that I'm passing around a little better, but you can see the detail you need to go into at the edge there to preserve that ground plane continuity. And then the thing to do to check you've got it right is just to do a coaxial cal to the coaxial ports of your 50 gigahertz vector network analyzer, and then measure the through path. And it is really, really surprising how little you need to do wrong in order for it to have some funny resonances in the 40 to 50 gigahertz band. But with care and attention to detail, a little bit of know-how, these work nicely to 50 gigahertz. So, some concluding remarks. I just thought I'd show this photograph of a PCB we did for one of our clients. I'm not allowed to tell you what it is, which is just as well, because I've actually forgotten exactly what it does. But it's a mixed, a multi-layer board. The top layer is Rogers 4003 1/8 thou thick, and then there's a number of FR4 layers. Another tip I'll give you is, be very careful. If you're just getting just Rogers 1/8 thou material, that's a really thin material. The board can be very flexible, and if you mount capacitors on it, you'll crack them. You have to be careful. So what we often do, even if we don't need much in the way of routing, is we'll put FR4 on the back for added rigidity. Here we needed some routing. Now, if I can get my laser pointer working, I'll point out a few things. Here, you'll see this is a Wilkinson splitter, and you can see it's a two-section Wilkinson because we were covering a broad bandwidth. Here is a little coupler here with a terminating arm here, and we couple some power off here. Here's a bunch of SMT ICs. Don't try and read the number because we took a lot of time and effort to blur it, so it couldn't be traced, but I'm sure you can guess who supplies these parts. These are actually band reject filters, a bunch of these here. You can see the microwave tracks. Now, another thing to mention is resist. We remove the resist over the microwave parts in order to have a better controlled impedance, to understand better what the impedance is. You can leave it on, but it does affect the dielectric properties. That is all I was planning on saying, but I'd be very happy to try and answer any questions anyone may have.